I'm pleased to introduce today's speaker, Ramiro Lafuente from the University of Queensland, speaking on homogeneous Einstein metrics via cohomogeneity-one approach.
All right, thanks, Caroline, and thanks everyone for coming. Yeah, first of all, apologies to those of you who have heard this talk already. And it's not extremely new stuff, but still relevant. We're still working on some generalizations of it. So, and feel free to stop me if you have any questions or comments, because I think I do have a shorter talk, so there should be plenty of time for comments or questions. Yeah, so the project is about studying homogeneous Einstein metrics, more specifically non-compact homogeneous Einstein metrics, using non-transitive actions on these spaces. It's kind of a weird idea. Doesn't sound too appealing, but then I'll try to explain why this makes sense. I guess you can see the little mouse thingy, right? So it's good. Yeah, so yeah, let's, this is of course a joint with Christoph Böhm from Münster. And yeah, the setup is as follows. I wanna work with a homogeneous Einstein space. So it's a homogeneous Riemannian manifold, meaning the isometry group acts transitively. So let's fix a transitive group G closed in the isometry group so that we have a compact isotropy group H, and then this homogeneous space is diffeomorphic to our manifold, and the metric G is going to be G invariant, meaning that the action of G is transitive and by isometries. And Einstein just means that the Ricci curvature is a multiple of the metric. So I'm going to use the notation Rich G interchangeably for the 0,2 tensor or the 1,1 tensor. So some examples of these spaces, any bi-invariant metric on a simple compact Lie group is Einstein. You can compute it explicitly. I always do that in my Riemannian geometry courses because it's possible to compute the curvature of such a metric. And then it was proved by Wang and Ziller that if H is maximal subgroup, in the meaning that it doesn't lie within any other proper subgroup of G, then the quotient G mod H admits a homogeneous Einstein metric. And then in the non-compact case, there are other examples which are also the symmetric spaces. So this bi-invariant metric is in particular a symmetric space in the previous compact case. In the non-compact case, I can mention the symmetric spaces such as SLNR mod SON or SLNC mod SUN, etc. And there are many other known examples, lots of them actually, just to give you a feeling that there are plenty of these guys, right? The main questions we are interested in are existence, given the homogeneous space, does it admit a G-invariant Einstein metric, uniqueness, up to isometry, of course. What are the geometric topological properties of these spaces, and etc., etc. I mean, there are other things one can ask about these spaces, right? So perhaps the most well understood case is, of course, the case where C equals 0, the Einstein constant is 0. That means that the space is Ricci flat, and then it was proved by Alexievsky and Kimmelfeld in the 70s that the metric has to be flat. So it's fairly well understood, right? Universal cover is a Euclidean space. Then let's move on to the compact case. So when C is positive, I would say the main open question in this setting, so the manifold has to be compact, and perhaps the main question is whether there are only finitely many Einstein metrics on a fixed homogeneous space up to isometry, right? So more specifically, there's this conjecture by Böhm, Wang, and Ziller in the GAFA paper in 2004, saying that if the rank of G is equal to the rank of H, so the true hypothesis is that the isotropy representation decomposes into pairwise inequivalent summands, and the space has an Einstein metric with positive Einstein constant, then there should be only finitely many such metrics, in fact. As far as I know, this is wide open even for SU2 cross SU2. We don't know, as far as I know, the number of left invariant Einstein metrics on that 6-dimensional Lie group. I think there are at least 2, but and there are no others with extra symmetries, say with more than a 6-dimensional group of symmetries. But that's about it. And then I will focus in this talk, of course, on the non-compact case. So when C is negative, the manifold has to be non-compact by a theorem of Bochner, saying that Ricci negative plus compact implies finitely many isometries, so it cannot be homogeneous. And so one can think that M, I mean, as a homogeneous space, it will be homotopy equivalent to a compact homogeneous space K mod H, where K is a maximal compact subgroup of the Lie group G. And now the main question in this case is the Alexievsky conjecture from the 70s, saying that, well, actually, M has to be homotopy equivalent to a point. So more precisely, M is diffeomorphic to Rn. So there will be like a dichotomy. If C is positive and it's a homogeneous Einstein metric, then it's compact. And if it's negative, then the space is contractible. So it's Euclidean space, even no fundamental group. Right? So let me comment on this problem a little bit in the following slide. Again, the setup, yeah, a non-compact, in this case, I already assume that the Einstein constant is -1, right? So non-compact homogeneous Einstein space. And the conjecture is that M has to be diffeomorphic to a Euclidean space. So what do we know about this problem? We know a lot, and at the same time, not too much, but let me mention perhaps some results in low dimensions and some results which apply to general presentation G mod H, don't make any assumptions on the specific algebraic structure of G. So it was proved by Nikonorow in 2005 that the conjecture is true in dimensions up to 5, provided there was a missing case, but it's not too difficult to see that this case cannot happen either. Then in 2014 and later in 2017, by work of Jablonski and Peterson, we have proved a certain compatibility of the Riemannian metric and the Lie bracket, so at the Lie algebra level, meaning that there is a sort of geometric Levy decomposition in the sense that the radical and the Levy factor which are of course Lie theoretical subspaces of the Lie algebra, they turn out to be orthogonal with respect to the Riemannian metric, right? So that's of course not true in general, and this has a lot of consequences. And then Mike and Peterson also proved that the group G, so the semi-simple part of the group G, cannot have any compact simple factors acting non-trivially. So all compact simple factors have to be contained in the isotropy. So for instance, that rules out the case. Let me see if I can write here. So for instance, the homogeneous space cannot be equal to, say, SU2 cross SL2R, right? Because this one has a compact simple factor. All right. And then with Romina Arroyo, we proved that, so using this structure result that I mentioned above, we proved that the conjecture is true in dimensions up to 8, provided that you exclude the case where H is trivial and G is a semi-simple Lie group. Okay, so there are a few exceptions, but in particular, in dimension 7, there are no semi-simple Lie groups, so the conjecture is true. This turns out to be useful for people studying special holonomy with symmetries, right? Because they typically imply the Einstein condition, and then you can use that the conjecture is true in dimension 7. In dimension 8, unfortunately, there are some simple Lie groups appearing. And then more recently, and actually applying the results that I'm gonna discuss today, my student drawing version proved that, so managed to push this 8 up to 10, which doesn't sound like too much of an improvement, but believe me, actually moving it 2 dimensions higher, there are a lot of homogeneous spaces in dimension 9 and 10, right? So this is truly amazing that the conjecture is true if the dimension is up to 10. And again, we cannot do anything about semi-simple groups. And there's also one exception, which is fairly complicated because of the number of invariant Einstein metrics that it has, which is this homogeneous space SP11 mod, diagonal embedded U1. But other than that, conjecture is true. So great news, right? And so, okay, so let me move on to discuss maybe what we know about these homogeneous Einstein spaces, so the ones that exist, because I'm talking about some properties of the low dimensional one, but what about in general? So now again, the setup is the same, non-compact homogeneous Einstein space. So all known examples so far, there are of a very particular kind, namely left invariant metrics on some simply connected solvable Lie group. So S is a solvable Lie group, and I'm gonna call these objects Einstein solved manifolds when the metric is Einstein. So first immediate observation, not immediate, but we should ask this is such an S diffeomorphic to Rn? Otherwise, we would get counterexamples immediately. But turns out that by induction, one can prove that any simply connected solvable Lie group is actually diffeomorphic to Rn, right? But of course, there are some homogeneous spaces diffeomorphic to Rn which are not solved manifolds, right? So they're not all of this type. I think the condition is that the isometry group has to be linear, or there's something like that, but I can't remember. And then let me mention that not only all known examples are like this, but there are a lot of known examples. And I would say, in a sense, much more than in the compact case. So the non-compact case allows for a lot more of freedom by varying the Lie group structure and all that. There's much less rigidity, which is obvious if you look at classifications of semi-simple Lie algebras on one hand and nilpotent Lie algebras on the other hand. I mean, there's no such classification for the latter. So as an example, there's a 46-dimensional family of homogeneous Einstein spaces in dimension 16, which are all the formations of this hyperbolic quaternionic space, quaternionic hyperbolic space, sorry. This was found by Heber, and there's nothing special about 16. I'm just giving a specific example. He understands the moduli space around rank 1 symmetric spaces. So there's a lot of examples, right? And then Jens Heber in his habilitación and later in an Invenciones paper in 1998 proved a lot of amazing properties for these spaces, namely uniqueness. So if you fix the S, it admits at most 1 up to isometry Einstein metric. And he also obtained geometric and algebraic properties. There's like 9 or 10 main theorems in that paper. So really a lot of information, provided that the Einstein metric satisfies a compatibility condition relating the Lie bracket and the geometry called standard. So standard means that if you look at the inner product induced by the metric on the Lie algebra, S, and then you look at the nil radical, so the maximal and nilpotent ideal, then the orthogonal complement of the nil radical, which is something defined in metric terms, not in Lie theoretic terms, has to be a Lie subalgebra. Right? So this is a compatibility condition between algebra and geometry. Right. Then later in 2010, perhaps earlier, but it was published in 2010, Jorge Lauret proved that all Einstein solved manifolds are standard. And this is great news because then they all satisfy Heber's fantastic properties like uniqueness and all these all these properties that I haven't mentioned, but are there in the paper. And so that's great news, right? And then, so our main result in this talk is, again, the setup is the same, non-compact homogeneous Einstein space. And our main result with Christoph from last year is that assuming that the manifold is diffeomorphic to Rn, then it has to be isometric to an Einstein solved manifold. Okay. Then by Lauret's result, it's in a standard Einstein solved manifold, and then all the known properties of Hilbert apply to any homogeneous Einstein space which is diffeomorphic to Rn, right? So yeah, so I should comment on why this is an interesting theorem. And to me, it's great, but perhaps it's hard to sell at the very beginning because you are assuming the conclusion of the Alexievsky conjecture. So it doesn't seem to help too much to deal with the conjecture, right? But to give you a hint that this is not, in fact, the case, let me mention this corollary, actually corollary of the proof, not of the statement a priori, is that this semi-simple Lie group SL2, K copies of SL2R, so SL2R to the K, does not admit any left invariant Einstein matrix for any K, right? So this was not known even for K equals 2 before this paper. So that was one of the exceptions in our classification in low dimensions. And now we can prove it for any K, right? And in fact, more is true, and this is what Rowan uses in his classification in up to dimension 10, is that as long as you have one SL2R factor acting freely or almost freely, then the space does not admit a left invariant Einstein matrix, right? So yeah, so that's something, because I mean, so before this we couldn't deal with any like purely non-compact semi-simple Lie group. So at least now, yeah, as a corollary of the result, we can prove this. And these are sort of related because if the universal cover of SL2R is R to the 3K, I guess, right? So if you would have an Einstein metric downstairs, then the lifted metric to the universal cover will be Einstein as well and left invariant. And I think that it's isometric to an Einstein solved manifold. I mean, it could be, but well, it turns out that it isn't, right? Sometimes some metrics on semi-simple Lie groups are isometric to solved manifolds. This is not always the case, but anyway. So yeah, are there any questions so far about the statement or the corollary? Is everyone still there? I don't want, now I'm terrified that the same that happened to Martin happens to me. So
we are here, we are here.
I see everyone there. Yes, cool. Okay. Okay. So now let me mention a few things about the proof, and then I'm gonna focus on explaining it in more detail in the next few slides. So as I said at the beginning, the remarkable thing about the proof is that one has to look at non-transitive actions on these homogeneous spaces, right? Which a priori it sounds nuts. So let me tell you why this is the case. Why do we have to look at non-transitive actions? And it's just like a way of convincing you that it makes sense. I mean, so the key idea is that we do have some estimates, which I call powerful estimates, because they've worked really well in many cases. So for instance, for studying the Ricci flow and even for studying Einstein metrics. They appear in Lauret's paper to prove that they are all standard. And these estimates for the Ricci curvature, they are sharp in the Einstein case, but unfortunately they don't give any information whatsoever when G is semi-simple, right? And of course we said that this is a hard case, and say one wants to understand whether this SL2R to the K admits Einstein metrics or not, then the estimates don't give you anything, right? They are void in this case. Now the idea is, okay, assuming that the homogeneous space is diffeomorphic to Rn, and in addition G is semi-simple, then we can understand these spaces fairly well. I mean, we can classify them. They are classified, not by us, but by other people 50 years ago. And then we can show that there's always a codimension one. Not codimension one, sorry, but there's always a subgroup of G which is non-semi-simple, which acts on this homogeneous space with codimension one. And this is written in as this because the isotropy of that action will be the intersection of H with G bar. So we always have a cohomogeneity-one action on this space, right? And then, well, we focus on studying cohomogeneity-one Einstein spaces where the transitive, so the symmetry group is not semi-simple, and hope that after paying the price of moving from an algebraic equation to an ordinary differential equation, one can still say something to conclude the theorem, the non-existence, right? So that's the key idea. Okay, so let me start by discussing the proof. And for simplicity, I'm gonna discuss the proof of the corollary without even mentioning the main theorem at the beginning, because I think all the main ingredients and ideas are already there. And even if you put k equals 2, still, I mean, if you can do the case k equals 2, then you can prove the main theorem in a finite amount of time. So yeah, so suppose that this group G admits a left invariant Einstein metric, the Einstein constant -1. Up to scaling, we can always choose this constant to be -1. And let's take this codimension one subgroup. So we'll replace the first SL2R factor by this Borel subgroup of upper triangular matrices in SL2R, right? So it seems that this is 3-dimensional, but we are in SL2R, so the determinant condition makes it 2-dimensional. And it's a solvable subgroup because, I mean, upper triangular matrices, right? I mentioned here that this group is non-unique in the sense that one can take a different basis for R2 so that, I mean, you can conjugate this with elements in SL2R and obtain isomorphic groups, right? Which will play a role later on. So there's not a unique B one can choose. There's a unique one up to conjugation, but it's important that there's many of them. So then we have a homogeneity-one situation because G bar being codimension 1 on G acts by left multiplication on this Riemannian manifold freely without isotropies and isometrically. And moreover, the quotient space, the orbit space is homeomorphic to S1 because it's essentially the SO2, the orthogonal matrices here that we are missing out, and that's S1. So the picture is as follows. It's not the best picture but you take an orthogonal, a normal geodesic. So these planes here, they represent the G bar orbits. So these are hypersurfaces in our ambient space, right? Codimension 1 submanifolds. And then you pick a point, and then you take a normal geodesic, and because the action is isometric, this normal geodesic will stay perpendicular to all hypersurfaces for all times, right? And because the space, the quotient is S1, you have to come back to the same orbit, although perhaps at a different point, right? This is not necessarily a closed geodesic, but still, this is the picture. I mean, this, of course, this is a homogeneous space, right? Because it's essentially a left invariant metric on G bar, right? So then we call, yeah, this is what I say here, right? So we call sigma t the hypersurface given by the G bar orbit at the point gamma t. Of course, these are periodic, right? Because at capital T, I came back to the same hypersurface. And then the metric G on the ambient space induces on each hypersurface a Riemannian metric, which is, of course, invariant under the G bar action. So since the G bar action is free, then they will be left invariant metrics on G bar after identifying, this hypersurface with G bar by identifying this point gamma t with the identity of G bar. So we have a curve of left invariant metrics on G bar, right? So that's given to us from the ambient metric. And then the question is, how does the Einstein condition for G look like for this curve of metrics, right? And spoiler alert, it's not going to be an algebraic equation in terms of the Lie bracket coefficients as in the homogeneous setting, but it will have some derivatives with respect to t. So it will be an ordinary differential equation. So things are a lot more complicated a priori. So first of all, let me introduce the shape operator. This is an extrinsic curvature, the shape operator of the hypersurfaces, which one can define by looking at how this one parameter family of metrics vary along this normal geodesic. Then one can write this derivative as 2 times G evaluated at, while you sneak in this self-adjoint endomorphism, Euclid shape operator. And this is perhaps not the most standard definition of shape operator, but the reason I do this is because I want to understand what conditions do I have on this curve of metrics. So I say that the first derivative doesn't tell us anything other than defining this extra piece of data that we have to take into account, the LTs, right? And now the second derivative, or in other words, the derivative of the shape operator, so this is covariant derivative, but we are thinking in terms of operators acting on the Lie algebra of G bar, so I mean, there's no problem with defining this, just the usual T derivative. So the derivative of the shape operator is given by the following curvature expression. So there's a multiple of the shape operator itself, plus the Ricci curvature of G bar. Remember, this is a homogeneous metric on G bar, right? Plus the identity in the Lie algebra. Oh, this is a typo. This should be the Lie algebra of the Lie group G bar, right? So the identity on these tangent spaces of the hypersurface. So I write it in orange because this is the Einstein condition, precisely. That this identity appears here is precisely telling us that the Ricci curvature of the ambient space restricted to the hypersurfaces is given by minus the identity, so to speak. And we call this a second order Ricci flow because essentially this is the second derivative of the one parameter family of metrics GT, and then the Ricci curvature appears, right? Plus some other terms, but this is sort of like a second order Ricci flow, right? And this is not such the weird idea to think about this as a second order Ricci flow. Again, I think of all these endomorphisms as endomorphisms of the Lie algebra of G bar, because this is naturally identified with the tangent space to the hypersurfaces at the point gamma t, right? By choosing killing fields, essentially. Yeah, and the reason this is relevant is that, well, the idea here, we try to understand this ODE. We're not going to be able to solve it explicitly, but at least we want to say something. And that something is we construct a monotone quantity, right? And the idea to construct a monotone quantity comes from the monotone quantities that we constructed for the Ricci flow of homogeneous spaces. They will work because of this particularly nice formula that we have here, expressing the tangential, so the Einstein condition on the hypersurfaces in terms of this one parameter family of metrics on G bar, all right? Okay, so we have this equation. We have to understand this ODE. And the first step is to simplify this already nice formula even better, even further, sorry. It will become better because of the following lemma. So these hypersurfaces are all minimal hypersurfaces, meaning mean curvature is 0 at every point. These are homogeneous hypersurfaces, so it's enough to prove it at one point. And that means that this trace of LT term will not be there because this is a mean curvature precisely. And then we'll get a much simpler ODE, only containing the Ricci curvature and the Einstein condition. Okay, so how does one prove this? Let me give you the full proof because not... Yes.
Yeah, may I ask you something?
Sure.
This property that it is a minimal hypersurface, it depends on the Lie group, D bar, or that you choose that.
It depends on the group, on the algebra G more than, I mean, it's not true in general, if that's the question. I will comment on this later. I want to say that, but I'm not entirely, yeah, I want to say if you take a codimension 1 subgroup in a unimodular Lie group, then it's true.
Okay.
And
sounds good.
I'm just thinking right now from the top of my head, that's, yeah, codimension 1 subgroup in a unimodular Lie group. That's all you need, I think. So we'll see the full proof here. So I think the proof works. So how do you compute the, yeah, sorry, was there any other question, Jorge? No? Okay. Yeah, so we take a unit normal vector field. I can use a tablet. So unit normal vector field. So this here, it will point in the other direction, right? So this is n. So of course this n is not going to be a killing field for the isometric G action, but it's normal to the hypersurfaces. And then you compute the shape operator by looking at nabla n, right? So that's the shape operator, and the trace of the shape operator is just nabla xi n xi. And I can sum over xi's in G bar, and I'm missing out one dimension here, but of course nabla n is 0, so that's why this is the full trace. Now I use the compatibility of the Levi-Civita connection at the metric because n is perpendicular to xi's, because the xi's, I change the color here to make it more didactic. And then the xi's are here, right? So they are orthogonal to n. And therefore I can pass this to the other side with a minus. And then this expression here is tensorial in n, meaning I can replace n, which was a unit normal to the hypersurfaces, by something that I want at this particular point. I'm looking at gamma t, so I replace this n by some killing field whose value at the point gamma t is the same as the value of n, right? And why do I do that? Because then I want to use the formula for the Levi-Civita connection on killing fields, given, for instance, in the Besse book, which tells you that this, if n is a killing field, and I am allowed to take it as killing field at this point, then we get this formula, where this is the Lie bracket in G, right? The algebra of big G. And this is, of course, a trace of the alt-joint operator n tilde, which is 0 if G is unimodular. So I think the only thing you need in this proof is that G is unimodular. And then these are minimal hypersurfaces. So it's quite common that you see this happening, this homogeneous hypersurfaces being minimal in Lie groups. All right. Yeah, I hope I convinced you of that. So that's a simplification that we can get rid of that first term in the formula, right? So what did I do? Oh, okay, so now I got rid of this, right? But I still have to understand the other terms, right? And for understanding Ricci, I come back to when I indicated the proof of the main theorem, and I have to use these estimates for the Ricci curvature, which in fact come from geometric invariant theory. So I'm not going to discuss how does one get these estimates. I'm just going to mention how they look like. So the setup here is take a Lie group with a left invariant metric, connected Lie group. Then the Ricci curvature, and this is true in homogeneous spaces in full generality, but I don't want to get too technical with isotropies, decomposition, etc., etc. So I just mention it in the case of Lie groups. The Ricci curvature can be decomposed as a sum of two terms, something that I call the modified Ricci curvature, Rich star here, and then this other term, -1/2, the symmetric part of this H vector here, where H is also called the mean curvature vector of this homogeneous space, and it's implicitly defined by being the unique element in the Lie algebra, such that this equation is satisfied. So in particular, if the Lie algebra of G bar is unimodular, if the Lie group is unimodular, then this term is not there, and the Ricci is just equal to the modified Ricci curvature. But in our case, it will never happen that the Lie group G bar is unimodular, in fact. And why is this a natural decomposition? Well, it is natural because this modified Ricci curvature has the property that it's orthogonal to the derivations of G bar. And I mean, on left invariant metrics, there's a natural gauge group acting, giving you isometric metrics, and that's the automorphism group of the Lie algebra, right? So two metrics, G bar on the same automorphism orbit. So G is H dot G tilde, where H is an automorphism. Then G is isometric to G tilde for left invariant metrics on this Lie group, right? So there's a natural group giving you isometric metrics. So somehow the most relevant part of the Ricci curvature when you're looking at evolution equations of left invariant metrics is the one which is perpendicular to the orbits of this automorphism group. And that's why this is the relevant part of the Ricci curvature, which you don't see in the unimodular case. So in the compact case, you always have this Rich equals Rich star, but in the non-unimodular case, you have to somehow forget about this other term. And the reason is that for this modified Ricci curvature, which is more natural, we have the following estimate. And the estimate goes as follows, given, so fixing the Lie group G bar. There is a set of natural numbers, which I call beta plus, so n natural numbers, such that for all left invariant metrics on G, and this is the important quantifier, for every left invariant metric simultaneously, we have this estimate for the Ricci curvature. So this is somehow like a weighted scalar curvature, right? So I'm weighting the scalar curvature with these coefficients, integer coefficients here, non-negative integers, right? Of course, I have to choose the right orthonormal frame so that, but I mean, this is just a technicality, right? Choose the right gauge, so to speak. But essentially, the weighted scalar curvature is always non-negative, right? And equality implies that the Lie group with left invariant metric G is standard. That my definition of standard doesn't use the solvable condition on the Lie algebra, so I just define it in the same way as before. Of course, here I'm using the 0,2 Ricci curvature, and before I used the 1,1 Ricci curvature. These are the same up to using the metric to raise or lower indices. And most importantly, beta plus is identically 0 if and only if the group is semi-simple. So in the semi-simple case, this doesn't give us anything. In the non-semi-simple case, it gives us a condition which is sharp on implying standardness, right? So let me get rid of this. So let's go back to the ODE that we had, and now we construct a monotone quantity for this ordinary differential equation. So if you look at the norm of the mean curvature vector with respect to the corresponding metric, you call this little h of t, then an easy sort of maximum principle, you look at second derivative. This is important here that the S1 here is compact. And then little h is always bounded by the trace of this. So by this, I mean the sum of the beta I plus, right? So now I want to think of as beta plus as the diagonal endomorphism of the Lie algebra instead of just a vector of integers. And now the idea is to consider this quantity, the weighted mean curvature. So instead of taking the mean curvature, which is a trace of L, which is 0, we take the trace of LT against beta plus. So we weight it with these n weights here, given by our Lie group, G bar. And then it turns out that this quantity is monotone along TODE, and equality implies standard, right? Okay, so what's the proof? One line proof. Of course, I didn't prove all the other estimates, but so F prime is this trace of L prime times beta plus, which is constant. Then L prime is Ricci plus identity. The identity is reflected in this last term. And the Ricci has two parts, the Ricci star and the part involving H, which becomes this term here. And then the maximum principle tells us that these last two terms are non-negative, and the GIT estimate tells us that this is non-negative, and so this is non-negative, and equal to 0 implies that the first term is equal to 0, and therefore standard, right? So that's the proof essentially. And why this is great news? Because S1 is compact. So we have a function which is periodic and monotone, and that doesn't go well together, right? So therefore, F has to be constant, right? Periodic and monotone, constant. And therefore G bar, say with the first metric, G bar 0 is standard, right? And why is this useful? Well, this means that the orbit of the last k-1 SL2Rs is orthogonal to the orbit of the nil radical of P. So this is a one-dimensional Lie group, right? 1, 1, 0, star. This is the nil radical of the group B that I mentioned here, defining G bar, right? So there's one dimension here in the first SL2R factor, which is orthogonal to all the others, right? But then I can change B, and then I get different ends. And then if I get 3 linearly independent directions, which are orthogonal to this, then I can conclude that the full SL2R first factor has an orbit which is orthogonal to all the others SL2R factors. And therefore, this is a Riemannian product locally. But since this is Einstein, then each factor has to be Einstein, but SL2R doesn't have any left invariant Einstein metrics. So this is a contradiction. And that's essentially the end of the proof of the corollary. Okay. And the main thing was to construct this rigidity, to obtain this rigidity via a monotone quantity. All right. So let me mention, I don't know, when did I start? 3 minutes past. So do I have 5 minutes, Emilio, Caroline?
Yeah, that's fine.
Okay. So let me mention some remarks on the general case. So I was only discussing this SL2R cross SL2R case, but in general, you must consider all presentations of Rn as a homogeneous space. Some G's will not be semi-simple. And you have to prove that after passing to a discrete quotient, you must have that this codimension one this cohomogeneity-one action with S1 orbit space. So it's fundamental that the orbit space is compact. And of course, you're not gonna get a compact orbit space on Rn by topological reasons. So that's why you have to pass to a discrete quotient. So in the case of SL2R, this is R3, and then you consider the actual SL2R, which is a discrete quotient of this simply connected Lie group. And then here we argue as before. In general, as I mentioned before, sigma t is not gonna be minimal. So instead of proving minimality, you have to prove that the Einstein condition implies that the orbits are minimal on average. We call this integral minimality. And the theorem that makes everything work is the following. So we have a homogeneity-one manifold, which is integrally minimal, where the orbit space is S1. And it's Einstein. Actually, it's enough to assume that it's Einstein only on the orbits, tangent to the orbits, say. Then all the orbits are standard. Right? So you can think of this as a homogeneity-one generalization of Jorge's result, because if you apply it to the Riemannian product of S1 cross an Einstein solved manifold, you get that this factor has to be standard. Right? And this is what makes the theorem work in full generality. This understanding of homogeneity-one manifolds with few assumptions, right? And yeah, so before I finish, let me comment on future directions, work in progress, so to speak. So can we apply this to more general situations? That's the hope. And let me comment on the hardest case of the semi-simple Lie group G. Now you look at the Iwasawa decomposition, where K is a maximal compact subgroup, and then this B, which I define to be AN, is solvable. Then we have any left-invariant metric on G induces a Riemannian submersion where the orbits are the orbits of the B action on G by left multiplication. And the quotient space is G mod B, which is homeomorphic or diffeomorphic to K. So it's compact. So remember that the fact that the quotient was compact was crucial in the previous argument. So here we want a compact quotient again, and we want an orbit which sort of we understand from the homogeneous point of view, right? So solvable in Einstein, this is better understood than semi-simple in Einstein in the non-compact case. So that's why the orbits being solvable Lie groups with left-invariant metrics is a good thing. So whenever you have a Riemannian submersion, you can decompose the tangent space as a vertical part tangent to the orbit of the group B, and the orthogonal complement, which is a horizontal part. Then this distribution is in general not integrable. And again, as in the homogeneity-one case, the metric G induces a K parameterized family of left invariant metrics on B. Before it was like an S1, now it's K, compact Lie group. And then the formulas from O'Neill tell you that the curvature of G can be expressed in terms of the curvature of B and the curvature of K, and two invariants, so two tensors here, two 1-2 tensors or 2-1, I don't know. So the first one is the tensor T, encoding the information about the second fundamental form of the orbits, and the second tensor A encodes the integrability or not of the horizontal distribution H. And then if you look at any textbook, it will tell you that the Ricci curvature of the ambient space, say in the directions which are vertical, can be written as the Ricci curvature of the corresponding fiber plus something depending on T and A. And this is not an algebraic expression necessarily. There might be derivatives, divergences, etc., but depends on T and A. And then, and on the metric G, of course. And then in the vertical horizontal directions, the same happens, and the same in the horizontal direction, right? So then you can hope that perhaps assuming Einstein on the ambient space gives us something on this family of left invariant metrics. That's the hope, at least. But there are a few problems, and I'm being honest with you, there are a number of problems, in fact. First of all, the Ricci curvature, this formula is not going to be an ODE anymore because K is higher dimensional in general. So this is a PDE for this family of metrics. In fact, second order elliptic PD. It's likely that, unlike in the case of homogeneity-one, using only this part of the equation, the vertical part, will not be enough. So one has to look at other parts. And it's not so clear what's the analog of integral minimality. I mean, there you can say, well, you integrate the mean curvature vector, but that's not the right thing to do for a few reasons. So remember, we had this assumption in the previous theorem, so one should find something analog in this general case. And I mean, the horizontal distribution, which in the previous case was one-dimensional, so of course integrable, might be non-integrable. So we have this extra tensor A here appearing in all the Ricci curvature formulas and changing things dramatically. And last but not least, the base is not flat. It's not an S1. And it's not even homogeneous. So the Ricci curvature here, one has to control in some way or another. And yeah, that makes it sound even harder. But we still have hope and we keep working. So yeah, thanks all for your attention and feel free to ask questions.
Thank you for a really interesting talk. Are there questions?
Ramiro, I have a question.
Yeah, hi Wolfgang.
Hi, how are you? So you mentioned that at some point you used the fact that the group was unimodular, but then you said that it doesn't really matter in the end. Why is that? You get an extra term in the Ricci curvature for if the group is not unimodular, right?
Yeah, so the reason it doesn't matter, the ambient, I mean, I used it at this point where the ambient group is unimodular to get the minimality.
Right.
Let me go back here, right? So to get the minimality, so then I said, you don't always get minimality, and that's precisely the reason, because this Lie group, the main Lie group cannot be, it's not unimodular in general. The reason it doesn't matter is because of the, I mean, you look, if G is semi-simple, then it's fine, right? If it's not semi-simple, the solvable part, which is what could make it non-unimodular, you can control very well metrically because of the structure theorems that I mentioned at the beginning, that we have this orthogonal Levy decomposition. So in the general case, we have to use this because once you control the solvable, the radical, so to speak, metrically to compute, you know, mean curvature and all that, then that part doesn't matter anymore. And essentially you can reduce to the case where G is semi-simple. But even then, if there's isotropy, then this computation is wrong. I spent a few months, if not years now, a few months trying to generalize this computation in general with isotropy, because my philosophy is that when you can do it for Lie groups, then adding isotropy is just a technicality, but in this case, it's not a technicality. I mean, the isotropy is constant along the normal geodesic, right? So it's the one G mod H, fixed H, everything. It's not true. There's some example. You can look at this SO2N mod SON. This is a homogeneous space, very simple one, where you can find metrics with, I mean, there's a cohomogeneity-one action by a certain group, the Borel subgroup, so to speak, but the orbits are not minimal. But, and they are not integrally minimal, but the Einstein condition forces it. Yeah, this is the hardest.
This minimality is the same thing as saying that the volume distortion is constant, right?
Yes, so
and
somehow
that's something you wouldn't expect in any more general situation.
These 2 points here, they have to lie on the same. So this group G bar has a codimension 1 subgroup, which is unimodular. So the G bar is non-unimodular, but it has a unimodular codimension 1 subgroup by removing this H vector that I mentioned. And so the condition that the integrally minimal is essentially that you come back to another point which is on the same G uni orbit of the starting point. So in particular, if the orbits are If the orbits are periodic, so if the geodesic is periodic, then it's automatic because of what you say, the volume distortion. You just come back to the same thing, so you can integrate logarithmic derivative or something like that. Mm. But yes.
But this doesn't happen in general, that the geodesic is closed, right?
No, not even for space. It's not true. No, we thought it would, but then we asked Burkhardt, and in 1 second he said, "Of course not," and he pointed out to the right reference. Yeah.
Well, I mean, in general, for one manifold,
homogeneity in the cohomogeneity-one setting, you can make this geodesic do whatever you want. Essentially.
Right.
You can make it come back to any other point in this space, right? But exactly. Even with homogeneity of the ambient space, for this example, because this example has isotropy decomposition, it has one trivial factor, and then it has two equivalent summands here. So that's why it's special. You have a number of metrics.
Okay.
Well, you can, yeah. The Einstein condition makes it work, actually. That's the most subtle point of the proof.
Okay, thanks.
Ramiro, this
okay.
n tilde,
yes.
which is a killing, but
yes.
if G is not semi-simple, maybe n tilde is not in G. It can be one of these skew-symmetric derivations. What?
So n tilde, yeah, if G is not semi-simple, you have to prove that n tilde is orthogonal to the radical.
Oh, okay.
Okay. Does it make sense? Because then it will be in the unimodular part, so to speak.
Okay, but I mean, why is in G? Because you have...
Because no, the reason it's in G, it's because G, I mean the group G acts transitively on this space. So on infinitesimally, that means that the Lie algebra G, if you act with the Lie, I mean by this I mean take all vectors evaluated where X is in the Lie algebra of Killing fields, right? This span the whole tangent space by homogeneity. So for any direction, even this direction, you can find a Killing field whose value at gamma naught is that direction, just by homogeneity. Okay.
Okay, yes, but you can find one in G.
You can find one in G.
Okay, okay. Because I'm worried about, because there could be more Killing vector fields, these skew-symmetric derivations. When
yes,
G is
but
not...
I'm not using. Yeah, I'm only using the transitive. Yeah, okay. That's true. Of course, there are many. Yes, but since this G already acts transitively, you can find it with the Lie algebra of G.
Perfect.
Yes. It's non-unique for sure. If they're isotropy, then and in general in the full isometry group, there will be freedom to change it. Yes.
Oops, I'm sorry, I disconnected for my system froze for a second. Are there any other questions, or what was the last question answered? I'm so sorry.
Sorry?
Was the last question completed? I'm sorry,
yes,
my Zoom crashed on me. So, so if there's other questions, thank you for a great talk. And our next talk is in 2 weeks. It'll be Alberto Rufero at so October 14th at 12:00 p.m. UTC time. Thank you.
Bravo.
Thank you.